The loudness of sound is measured on a logarithmic scale called the decibel scale. The loudness B of a sound, measured in decibels, is defined as B equals 10 times the logarithm of I over I naught, where I naught equals 10 to the negative 12 watts per square meter, is the intensity level of a sound that's barely audible. Find the decibel level of a jet engine during takeoff if the intensity was measured at 100 watts per square meter. Find the intensity level of a motorcycle engine if its loudness was measured to be 90 decibels. We're going to look at these two problems one after another, but both of them rely on the same equation, B equals 10 times the logarithm of I over I naught. Now, in our first problem, when we're looking at the decibel level of a jet engine during takeoff, we're told the intensity is 100, and we also know that I naught is 10 to the negative 12th, so this becomes 10 times the logarithm of 100 over 10 to the negative 12th. Now, we can take this negative exponent and make it positive by moving it to the numerator. This gives us 10 times the logarithm of 100 times 10 to the positive 12th. Now 100 is 10 times 10, which is 10 squared. So we can rewrite that as 10 squared times 10 to the 12th. And we know from our rules of exponents, we can combine those to get 10 to the 14th power. So we have 10 times log of 10 to the 14th. Now, if we look at this logarithm here, the log base 10 of 10 to the 14th, this is asking 10 to what power is equal to 10 to the 14th? And of course, the answer is 14. Effectively, taking the log base 10 and raising 10 to a power cancel out, and we're just left with 14. So this becomes 10 times 14, which is 140. And so that sound is 140 decibels. Let's take a look at the other problem. It's going to use the same formula, but here it's a different sound, so we'll have different values for our variables. So here we're looking at a motorcycle engine, and we're told that the loudness is 90 decibels. So we're given the loudness as 90, and we still know that I naught is 10 to the negative 12th, but what we don't know is the value of I. We're looking to find the intensity level here. Now, because we want to solve for a variable inside a logarithm, we're going to want to get the logarithm alone first, and then we can write it in exponential form to solve for our variable. So first, we want to get rid of this 10. If we divide both sides by 10, that gives us 9 equals log of I over 10 to the negative 12th. And now that we've isolated the logarithm, we can rearrange this and write it in exponential form. This is going to be 10 to the 9th power equals I over 10 to the negative 12th. Now, to deal with this 10 to the negative 12th in the denominator, we know, again, we can move it to the numerator so long as we make that exponent positive. So we've got 10 to the 9th equals I times 10 to the 12th. And then to get that I alone, we need to divide both sides by 10 to the 12th power. And on the left, when we have a quotient of two exponential expressions with the same base, we subtract the exponents. So here, 9 minus 12 is negative 3. So I is 10 to the negative 3rd power. And we can leave our answer like that because we've seen that oftentimes the intensities are measured as powers of 10. So 10 to the negative 3rd watts per meter squared is a perfectly acceptable answer. You could also figure this out. The negative exponent means it goes into the denominator, and 1 over 10 cubed is 1/1000th or 0.01. So these are also perfectly acceptable answers. All three of these represent the same quantity. The reason why we use the decibel scale is because it's much easier for us to understand the difference between 140 and 90 than it is to understand the difference between 10 to the negative third, 100, and 10 to the negative 12th. This is a situation where the intensity has such a wide range that it's difficult for our brains to comprehend it. So we use a logarithmic scale, which puts all of the numbers into a smaller range that's easier for us to understand.